Welcome to the deep dive. Today we're going to be talking all about gases. They're invisible forces that are literally everywhere.
Yeah.
You breathe them, they make balloons float, and some engines even run on them.
Yeah, you can't live without them.
But have you ever actually thought about what makes them so different from solids and liquids? And how they behave at a molecular level?
It's easy to kind of forget about gases because you can't see them. But once you start understanding their unique properties, it's kind of like a whole new world opens up.
Yeah. So let's start with the basics. What makes gases different from solids and liquids? I mean, we've all boiled water and seen it turn into steam, but what's actually happening on a super tiny level?
So the key difference is how much the molecules can move around.
Oh, okay.
In a solid, molecules are packed super tight, almost like a well-organized marching band. They're vibrating in place, but not really going anywhere.
Yeah.
And then liquids are a little looser, kind of like a group of friends mingling at a party, right? They can move around, but they're still pretty close together.
Uh-huh.
But gases, those molecules are like kids let loose on a playground, just zipping around with tons of energy and almost no restrictions. They have way weaker forces holding them together, so they spread out to fill any container they're in.
So it's the forces between the molecules, or the lack of them,
Yeah,
that makes gases act the way they do.
exactly. And because those forces are so weak, gases have a lot more potential energy compared to solids or liquids.
Okay.
That's what lets them expand and compress and, do all the things that solids and liquids can't.
Yeah, that makes sense. Now, I've always wondered about this. What's the deal with ideal gases? What makes them so ideal, and why do scientists use them to understand how gases work?
Ideal gases are basically the rule followers of the gas world.
Oh, okay.
They behave in a very predictable way based on some simple laws, which makes them really good for understanding the basic principles. In an ideal gas, we pretend that the molecules themselves don't really have any volume compared to the container they're in.
Oh, interesting.
It's like saying that the individual dancers on a giant dance floor don't take up any space at all.
So it's kind of a simplification to help us study them.
Exactly. This simplification allows us to make calculations and predict how gases will react when you change things like pressure, temperature, and volume. Of course, no gas is perfectly ideal in the real world,
Right.
but this model gives us a good starting point.
Okay, that makes sense. Now, what about those standard conditions that scientists always use when talking about gases? I've heard of things like STP and NTP. What are those all about?
Yeah, those are really important reference points. Think of them as like universal benchmarks to make sure everyone's on the same page when they're describing gas behavior.
Oh, okay, so like a universal language for gases.
Exactly. Standard temperature and pressure, which we call STP, is set at 0 degrees Celsius, which is also 273.15 Kelvin, and 1 atmosphere of pressure. And get this, 1 mole of any ideal gas, regardless of what it's made of, will always take up a volume of 22.4 liters at STP.
Whoa, that's kind of mind-blowing. So whether it's oxygen or nitrogen or something crazy like xenon,
Yeah.
1 mole of any ideal gas will always be 22.4 liters at STP.
That's the rule.
That's pretty amazing. What about NTP?
So NTP is normal temperature and pressure. It's similar to STP, but just a tad warmer. It's 20 degrees Celsius or 293.15 Kelvin, and again, 1 atmosphere of pressure. Basically STP, but at a more comfortable room temperature.
Got it.
Yeah.
So these standard conditions give us a consistent way to compare and understand different gases.
Exactly. They're the common ground for scientists around the world to talk about gas behavior without getting confused.
Okay, I think we've got the basics down, but let's go deeper. I'm ready to dive into the kinetic molecular theory. I feel like this is where things get really exciting.
Yes, the kinetic molecular theory. It's like peeking behind the curtain and seeing all those molecules doing their thing.
Ooh, tell me more. What are the main points of this theory?
Imagine a container full of gas molecules. These molecules are constantly moving around in random directions, like a swarm of bees buzzing around. They bump into each other and the walls of the container, and these collisions are perfectly elastic, meaning they don't lose any energy when they bounce.
So it's like a constant chaotic dance, but there's some order in all that craziness.
Right. And one of the key things the kinetic molecular theory tells us is that the average kinetic energy of these gas molecules is directly proportional to the temperature of the gas.
Oh, okay. So the hotter the gas, the faster those molecules are zipping around.
Exactly. Think of it like turning up the tempo at a dance party. The hotter it gets, the wilder the dancing. And the more those molecules bang into the walls of the container, the higher the pressure we observe. So pressure is a direct result of all those tiny collisions.
Okay, that makes sense. But those molecules are incredibly small, right? How can scientists even measure things like how far they travel on average or how fast they're going?
Well, we have some pretty clever ways to figure that out. For example, we have the mean free path, which is the average distance a molecule travels between collisions.
Okay.
It's like measuring the average distance a bee flies before it bumps into another bee in the hive.
Got it. So it's a way to measure the chaos in a sense. What about their speed? I imagine they're all moving at different speeds, right?
They are. That's why we use something called the root mean square velocity. It's basically a way to average the speed of all those molecules, even though they're constantly changing.
So it's like trying to find the average speed of a whole swarm of bees, even though some are zipping around like crazy and others are taking it easy.
That's a great way to put it. These concepts help us understand the statistical nature of gas behavior, and they're essential for making predictions about how gases will react under different conditions.
Okay, that makes sense. So we've talked a lot about how these gas molecules are constantly moving and bumping into things. But I'm curious about the energy side of things. What about the concept of degrees of freedom? That sounds pretty complex. Can you explain that one?
Sure. Degrees of freedom basically describe the ways a molecule can move and store energy.
Okay.
Think of it like this. A train moving along a track only has 1 degree of freedom. It can only move forward or backward.
Yeah, it's pretty limited in how it can move.
Right. But what about something more complex, like a drone?
Okay, yeah.
A drone can move up, down, left, right, forward, and backward.
Right.
So it has 6 degrees of freedom.
Oh, wow.
It can move and rotate in 3 dimensions.
Okay, so the more complex the object, the more ways it has to move and store energy.
Exactly. And the same goes for molecules. A simple gas like helium with just one atom only has 3 degrees of freedom because it can only move in 3 dimensions.
So it's like a solo dancer on that dance floor we were talking about, free to move in any direction.
Yes, exactly. But then you have more complex molecules, like those in diatomic gases.
Okay.
Diatomic gases, things like oxygen or nitrogen, are made up of 2 atoms bonded together. At low temperatures, they have 5 degrees of freedom.
Okay.
3 are translational, just like our helium atom, but they also have 2 rotational degrees of freedom.
Wait, so they can rotate as well as move through space? That's like adding a spin to their dance moves.
You got it. And as things heat up, they get even more moves.
Wow.
At higher temperatures, diatomic gases gain 2 more degrees of freedom, bringing the total to 7.
Okay.
These extra degrees of freedom are vibrational, meaning the 2 atoms in the molecule can vibrate back and forth, kind of like they're connected by a spring.
Wow, so the way these molecules move and store energy gets even crazier as the temperature rises.
Exactly. And that brings us to another important concept, the equipartition of energy.
Okay, I'm intrigued. What does equipartition mean when it comes to these dancing molecules?
It means that a gas's total kinetic energy is spread evenly across all its degrees of freedom. Oh, interesting.
So each degree of freedom gets an equal share of the energy pie, so to speak.
So if we have a diatomic gas at a certain temperature, each of its 5 degrees of freedom at that temperature gets the same amount of energy.
Exactly. It's a very democratic distribution of energy. And this equal sharing of energy is directly related to the temperature of the gas. The higher the temperature, the greater the average kinetic energy of the gas molecules. And the more those molecules are shaking and vibrating.
It's like a beautifully choreographed dance where the temperature sets the pace and the degrees of freedom dictate the moves.
That's a great way to visualize it. And understanding these basic concepts helps us to understand how gases transform and interact with their surroundings.
Wow, this is so cool. I can't wait to hear more about how these principles come into play in different thermodynamic processes.
Well, then let's jump right into the different ways gases can change. Each one has its own unique energy story. So let's kick things off with a process that's probably happening in your kitchen right now. Isochoric heating. Isochoric heating. That sounds kind of intense.
No, it's simpler than it sounds. Just imagine heating up a sealed container, like a pressure cooker.
Oh, okay.
The volume stays the same because the gas is trapped inside, but as you add heat, the pressure starts building up.
Right, right. Like when I'm using my pressure cooker and the steam gets trapped inside,
Yeah.
that's what cooks the food faster, right?
Exactly. At the molecular level, all that heat energy you're adding goes straight into increasing the internal energy of the gas. And that makes those molecules move faster and collide with the walls of the container more often and harder.
So it's like turning up the heat at our molecular dust party. Everyone's moving faster, bumping into each other more.
You got it. Now, let's switch gears a little bit and imagine a different scenario. Isobaric expansion. Think of a hot air balloon.
Oh, okay. I can picture that. The colorful balloon, the basket, the whoosh of the burner. But how does that relate to gas behavior?
Well, as you heat the air inside the balloon, it expands and pushes against the fabric, so the volume of the balloon increases. But the pressure inside stays pretty much the same because the balloon can expand freely.
So it's like giving those dancing molecules more space to move around in so they don't bump into each other as much, even though they're moving faster because of the heat.
You nailed it. And in this case, the heat energy isn't just making the molecules move faster, it's also doing work by expanding the balloon and pushing against the atmosphere.
That makes sense. Some of that energy is going into making the balloon bigger and lifting it up into the sky. Now, what about those processes where the temperature stays the same? Those isothermal processes. They seem a little counterintuitive to me. How can you change the state of a gas without changing its temperature?
Isothermal processes are definitely interesting. They involve a delicate balance between heat exchange and work.
Oh, okay.
Imagine you're slowly compressing a gas in a cylinder, but this cylinder is a good conductor of heat.
Okay.
Now, as you compress the gas, it would naturally want to heat up, right? But because the cylinder is such a good conductor, that heat flows out into the surroundings and that keeps the temperature constant.
So it's like squeezing a sponge underwater. The water absorbs the heat from the squeezing, so the sponge itself doesn't get hotter.
That's a fantastic analogy. In an isothermal process, all the heat energy that goes into the system is used to do work, like pushing against a piston or expanding against external pressure. None of it goes into making the gas molecules move any faster.
So in this case, it's all about transferring energy, not about making the molecules dance more energetically.
Exactly. Now let's flip the script. What happens when you compress a gas really quickly, so quickly that there's no time for heat to escape?
Okay, yeah.
That's what we call an adiabatic process, and things get a little more dramatic here. Picture a bicycle pump. When you push down on the pump really fast, you're compressing the air inside without giving it much time to exchange heat with the surroundings.
Right. I've definitely noticed that. The pump gets warm when I'm inflating a tire quickly.
Exactly. That warmth is a sign that the temperature is increasing because of that rapid compression. In adiabatic processes, no heat is exchanged with the surroundings, so any work done on the gas, like compressing it, leads to an increase in both its internal energy and its temperature.
It's like all that energy is getting bottled up inside the gas, making those molecules go crazy.
Right. And on the flip side, if you were to suddenly let a gas expand adiabatically, like when you puncture a can of compressed air, the gas would cool down rapidly as it expands and does work on its surroundings.
Oh, that makes sense. So adiabatic processes are all about those quick changes where heat doesn't have time to catch up.
You got it. They're kind of like the plot twists in the gas world where energy transformations happen really fast.
Now, we've talked about how gases can be compressed, expanded, and heated in all these different ways.
Yeah.
But what happens if you just let a gas expand freely into a vacuum, like where there's nothing to push against?
That's a great question. You're talking about something called free expansion, and it highlights a key difference between ideal and real gases.
Okay, I'm all ears. Tell me what happens when a gas gets to expand without any resistance.
When it comes to ideal gases, something pretty interesting happens. The temperature stays the same during free expansion. That's because there's no work being done against any external pressure.
Huh. So even though the gas is spreading out and taking up more space, its temperature doesn't change. Why doesn't it cool down as it expands?
Well, remember that in our ideal gas model, we're pretending that those molecules don't have any forces attracting or repelling each other, so they don't need to use up any energy to overcome those forces as they expand. It's purely a kinetic process.
Okay, that makes sense for an ideal gas. But what about real gases? They do have those forces between molecules, right?
You're right, and that's where things get a little more complicated with free expansion of real gases. Instead of staying perfectly constant, the temperature actually changes a little bit. And that's because those intermolecular forces do have an effect.
So how do those forces mess with the temperature during free expansion?
Think of those molecules as being a little bit sticky. As the gas expands, those attractive forces between the molecules weaken. And that change in potential energy can actually lead to a small change in temperature.
So free expansion is a perfect example of how those simplified models can only take us so far.
Yeah,
In the real world, there are always these little details that make things more complex and more interesting.
exactly. And those little details are often where we find the most exciting discoveries.
Right, the Carnot cycle. It sounds almost mythical, the most efficient engine possible. What makes it so special?
It's really a theoretical thing, a way to understand the limits of how efficient an engine can be when you're dealing with heat. No real engine is ever going to be perfectly efficient.
Right, yeah.
But the Carnot cycle gives us kind of a perfect example to compare things to.
So it's like a goal that engineers try to get as close to as they can, even if they can never actually reach it.
Exactly. The Carnot cycle has 4 parts, and they're all reversible. Isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression.
Okay.
Picture our gas trapped in a cylinder with a piston, like we talked about before.
I'm picturing it. All right, let's break
Yeah.
it down step by step. What happens during isothermal expansion?
So in isothermal expansion, the gas absorbs heat from a high-temperature reservoir while it's expanding and doing work on the piston. The important thing here is that the gas stays at the same temperature the whole time.
So it's like the gas is taking a little sip of heat energy from a hot bath and using that energy to push the piston outward.
Yeah, that's a good way to think about it. Then, during adiabatic expansion, we basically wrap the cylinder in insulation so no heat can get in or out.
Okay.
The gas keeps expanding and doing more work on the piston, but now its temperature goes down because it's not getting any more heat from that reservoir.
So it's like the gas is coasting downhill using the momentum from that hot bath, but it's starting to cool off because there's no more heat coming in.
Exactly. Then we move on to isothermal compression. Now the gas is being compressed at a constant temperature, but it's releasing heat to a low temperature reservoir.
So now we're squeezing the gas back down and it's dumping some of its heat energy into a cold bath.
Right. And finally, we have adiabatic compression.
Okay.
The cylinder's insulated again, and we compress the gas even more, but now its temperature rises because it's not losing any heat to the surroundings.
So it's like we're pushing the gas back uphill and it's getting hotter because it's working hard and there's nowhere for that heat to go.
Perfect analogy. At the end of the cycle, the gas is back where it started, ready to go through it all again. And what's really amazing is that this whole cycle could theoretically happen in reverse with no energy loss from friction or anything like that.
So that's why it's the most efficient engine possible. It's like a perfect scenario where energy is transferred and transformed without any waste.
Exactly. Of course, no real engine can ever be that perfect. There are always going to be some losses. But the Carnot cycle helps us understand how efficiency works at the most basic level.
That's amazing. So we've covered so much in this deep dive. We've talked about the kinetic theory of gases, those crazy molecular dances, all sorts of thermodynamic processes, and even this mind-blowing Carnot cycle.
It's been a wild ride through the world of gases, and hopefully now when you think about a gas, whether it's the air you're breathing, the fizz in your soda, or the steam from your coffee, you'll have a better understanding of just how much is going on at the molecular level.
I know I will. I've definitely learned a lot today. And to our listeners out there, thank you so much for joining us on this journey into the amazing world of gases. Keep those questions coming and never stop exploring the wonders of science.
And until next time, stay curious.